So first we need to define radians, and then we need to briefly recall graphs of trig functions, and we will study inverse trig functions and basic properties. Okay, so to define radian, let's consider a fan of a circle with radius 1. So you can think of the fan inside unit circle. We define radian so that the angle let me use theta for this angle. So the angle is exactly same to the arc length. Let me use L. So we have arc length and angle. So we define radian so that the angle in radian, if you measure this angle in radian, then this angle is exactly same to arc length. In other words, theta is L. So if you apply this definition to entire circle, so we have angle 360, right? And the perimeter of this circle, or the arc length of this big fan, is 2 pi 1, or 2 pi. So by definition, the angle, if you measure this angle in radian, this radian must be this perimeter. So the length 2 pi must be 360 if we measure this in radian. That's it. So we have very nice identity. 360 equals 2 pi. So this is how we define radian. You may ask, why we care radian? Well, there are many reasons. Well, eventually you will see nice properties of trig functions when you use radian. Eventually we will study derivative of trig functions and so on, and you will see nice properties. For example, so eventually we will see that trig functions have nice property when you use radian measurement. So for example, derivative of sine is exactly cosine. Well, this is true only when you use radian in this angle. If you use a degree angle, this identity is not true any longer. So that's one example, but eventually we will see nice properties when you use radian measurement. Okay, so quick example. First question asks how to find radian measure of 60. Well, you can use this identity. So you can use the ratio. So radian over degree. So from this identity, the radian is 2 pi. That corresponds to degree, 360. And from this condition, we are given 60. So 60, and we are after radian measurement, say x for this unknown. And we have exactly the same ratio. And one way to solve this equation is to take kind of cross product. You take product 2 times 60, so 2 pi times 60 is x times 360. So once you solve this, you will get x. So 6 times x is 2 pi, or x is pi over 3. Oh, pi over 3. Okay, so 60 degree corresponds to pi over 3. So conversely, you can transform radian measurement to degree. So 5 pi over 4, the same ratio. Radian expression, 5 pi over 4 compared to degree. So we are after the degree for this radian. And this has to be radian over degree. Again, you can take cross product like this. So that means 2 pi x is 5 pi over 4, 360. So after canceling, we have 90 times 5 pi is 2 pi. So 5 times 90, 450 divided by 2 is our x, is 225. Okay, so let us briefly review how we plot graph of trig functions. We are not going to spend much time on this graph of trig functions, but I'd like to point out how we use unit circle to plot the graph of sine, cosine, and tangent. So suppose this is a unit circle. You can pick a point here, say point P, x coordinate and y coordinate, like this. Okay, once you draw line joining the origin to the point P, you see right triangle with base along the positive x-axis. Say this angle is theta. Then by definition, sine is, well, trig functions are ratio of sides in this right triangle. So let me call this hypotenuse, and then adjacent, and then opposite. So inside on this right triangle, we have 3 sides: hypotenuse, adjacent, and opposite. So by definition, sine is ratio between opposite and hypotenuse. Now that we are using unit circle, this hypotenuse is nothing but 1. So if h is 1, this ratio becomes very simple, just O, or opposite, the length of this, or the height or y coordinate of this point. So this is simply y coordinate. So that means when you plot graph of sine, you take only y coordinate. So you can imagine your angles theta grows, increases, then you take only y coordinate for each angle, then you will get graph of sine. So similarly, cosine is defined by the ratio between adjacent and hypotenuse. Again, this becomes only adjacent if hypotenuse becomes 1. Now that h is 1, you simply take only x coordinate for this cosine. Again, when you plot the graph of cosine, imagine your theta grows, increases, then you take only x component, x coordinate for each angle, then you will get graph of cosine. For this tangent, we need a slightly different approach. So tangent is the ratio between opposite and adjacent over A. For this, it'll be great if this denominator a becomes 1, but this denominator is not 1, for example, in this triangle. So we want to have this a equals 1. In other words, we can fix this base 1. That means you extend this point so that you can extend this point to have, say, p prime. Then you can think of bigger right triangle, this guy. So you fix this adjacent so that this is always 1, 0. So this adjacent is fixed by the line segment from origin to 1, 0. Then as the angle grows, your triangle changes so that this height grows and so on. So in that case, you take opposite. I mean, not this opposite, but this opposite, say O prime. Okay. Unfortunately, we are not going to spend much time on this slide, but you can use a GeoGebra example to see how this idea helps you plotting graph of sine, cosine, tangent. You can click sine, cosine, and tangent in the PDF note that we provide.